Okay, so good day to each and every one of you. This will be part 3 of the shear moment diagrams for our initial beam that we have. This was the given. And our goal here is to construct the shear moment diagram and the internal stresses that was imposed on our beam. So based on our previous data that we have the formulas for the shear and bending moments for segment AB. We have here the formulas for the shear and bending moment for segment B-C, and then we replace the values of x's by their approximation 0 and 4. So we have 0 and negative 800, and for this one we replaced it by 4 and 14. For the bending moment, we have negative 800 if it was replaced by 4, and then we have 0 if it was replaced by 14. And for the shear loads, if we replace this x by 4, we have the value negative 680, and if we replace it by 14, we have the value of negative 520. So let's go here to our diagram. At this point here, at point A, okay, this is point A, this is point B, and this is point C. At point A, we have a load acting downward, so that should be negative. Okay, so we're going down 200, and after, or rather before going to segment B-C, there's no other loads that is imposed on this length 4. So we can simply say that we can move on without having any change because the 200 pound is still remaining constant, and we don't have any other forces that is interacting with this length from 0 to point B, which has a measurement of 4. So that's why we can just simply graph it like this, because there's nothing much is happening here. Okay, and upon arriving at point B, we have this upward load equivalent to 880 pounds. Means to say that we are going to, this is negative 200, we're going to go up 880 units. Okay, so 880 minus 200, that should be 680. If we are going to change the sign of this one, because initially this was going downward, if we're going to change the sign of this one, it will become positive if the direction is going upward. So, means to say, we have this 880 pound reaction here at point B going up. So, from negative 200, we're going to go up 880 units. So, 880 minus 200, that should be positive 680. So, changing the sign, that is going up. So, we're going up. So, this one is 680. Okay. And the next step for B to C, what we're going to do here is, since we have this uniformly distributed load, and let's check the shear formula that we have for B to C, which is 1160 minus 120x. So the degree of power for this equation is 1, means to say that is linear. So since all the way from B to C, we have this upward direction 520 at the support C, which means that from this point 680, we are going down 520 all the way to this point here, and because of that, we have this certain value that we managed to solve. If we replace x here by 14, it became negative 520. Initially, that was going down. If we change the sign, it would go up, so it would become positive. So let's go down from 680 all the way to negative 520, because we have this one. So doing that should be like this, graphing that one. Goes like that. So this one is negative 520, and we have this upward reaction for support C going up, so we are going back to 0. So this is the shear diagram for this beam. So this is the shear diagram for the shear for this beam. And the next one is to look for the bending moment diagram. And for us to do that, upon solving, starting here at segment A dash B, if we replace x by 0, so the answer is 0, so we're going to start at 0. And look at the degree of power of this equation, so it's still 1, so that should be linear. So it says here negative 200, and then replace it by 4, that should be negative 800. So by extending this line, going downward, and the degree of power of the equation is first degree, so that should be a straight line going downward. So this one is negative 800. So graphing it downward like that. So that's negative 800. And the next one is replacing this equation by 4 and 14. We have negative 800 pound-foot. And sum it up, if we are going to replace this equation, its variable x by 40, it became 0, which is correct. But how are we going to graph that information? Okay, there is a concept here in the shear bending moment diagram that if v is equals to 0, that is the point where we can locate the maximum bending moment. Okay, and how are we going to do that? Well, since that v is equals to 0 can be found here in our diagram for the shear diagram, it means to say that v is equals to 0. It means that v, or rather the slope of this diagram, is equals to 0. That is the location where we can find the maximum bending load. So how are we going to do that? Well, we're going to use this formula for the shear equation that we managed to solve for segment B dash C. Okay, so as I mentioned, if shear load is 0, that is the location where the maximum bending load can be found. Okay, so taking into consideration this formula, V is equals to 1160 minus 120x. So we equate everything to 0 so that we can solve for x. So 0 is equals to 1160 minus 120x transpose 120x equals to 1160, and then dividing both sides by 120. So 1160 divided by 120. So x should be approximately 9.667 feet. So this is the location from point A, where the measurement or the location of the maximum bending load can be found. Means to say, from this, from this point, measure it up all the way here. Okay, let's just project this line, and at this point, that is where v is equals to 0, we can simply project that downward. Projecting that downward, just like that. So the measurement of this from point A to here, that should be 9.667 feet. Okay, and from this point on, all we need to do is to solve for the maximum bending load. So how are we going to do that? Well, the solution for that one is simply easy. So let's just try to remove this excess space here on top, so that we can have some additional space for us to solve. Okay, it goes like this. Since we managed to already solve for x, can just simply remove this also. Okay, so now we have some additional space here. What we need to do next is to use this formula so that we can solve for the maximum bending moment. So M sub max is equals to this formula and replacing it by 9.667 feet. Okay, because this is the location from point A to this portion of the beam. As you can already see here on the diagram, that is going downward, and then this intersection line here, where at this portion, V is equals to 0, because that's constant, we can replace x here by 9.667. So negative 60, 9.667 squared plus 1160, 9.667 minus 4,480. So m sub max should be equivalent to approximately 1,127 pound-foot. Okay, so if that's the answer for the maximum bending moment, and don't forget that if we recall here on our formula for the bending moment, the power, the degree of power of this formula is 2, because we have this squared. Means to say it's like parabolic. We have this positive answer 1127 pound-foot. If this the degree of power of this formula or this equation is second, then this should be parabolic. Goes like this one. And this location is 1127 pound-foot. Okay, this one. And the next step is, since we arrive at 1127 pound-foot, the next step is to simply go back to 0. Because the degree of power of this equation is second, so that's why it's still parabolic. So this one is the bending moment diagram. So that's it for part 3 of this discussion. And I think there's no more to be simplified from this point on. No? So that's it.